So how confident are you in confidence intervals? Well, to this point, you've probably learned about confidence intervals for proportions. We're going to mix it up a bit. We're going to look at confidence intervals for means. All right? Now, recap, something you should have written down in your notes, the recipe for success when it comes to confidence intervals. Guess what? It's not changing. All right? I'm going to make this a little bit smaller so we can all fit on here, but we are still expecting you to define a parameter, name the thing that we're doing. In this case, it'll be, depending on what it is, one sample proportion or confidence interval for means today. You have conditions that you have to check. There's a formula to find the actual confidence interval, plug in the numbers, make the interval, and interpret. Okay? Since we're dealing with means now, let's do a quick recap of what we learned about sampling distributions for means. So, the shape. Ideally, we're looking for normal, but we'll actually be looking for normal-ish. But let's just see. The shape. We'll say the shape is approximately normal if, what did we learn? Two different things. Population is normal. That's one thing. If you know that, then you can just be good. Or you can look at the central limit theorem. So if n is greater than or equal to 30, that's that central limit theorem. Then we know it's also going to be approximately normal. So that ends up being one of our conditions too. We want to look for a normal or approximately normal shape. Otherwise, I'll make one note for today. If we don't have enough information for either of those, we're going to make one more option. If the sample distribution shows no skew or outliers. We're not going to go out and say it's normal, but we're going to say it's good enough to be approximately normal. All right, so that is one of our conditions. What do we know with the center? If we have the mean of a sampling distribution of means, it's going to be equal to the mean of the population. Variability. Okay, remember the standard deviation of these means is going to be equal to population sigma over the square root of n. And then we can utilize that in our formula for a confidence interval, right? So we've gotten into confidence intervals to this point, but we did it with proportions. Remember, our confidence interval is really the statistic, which now is going to be our x bar plus or minus the z star times sigma over square root of n, because we're using this in there for that standard error. Now, there's one thing that's going to be a little bit different with means, and it's this right here. Okay? So we're going to use this thing called a z or a t distribution. And this visual over there kind of helps. When we're trying to estimate the mean of a population, not proportions, means, we also have to estimate the standard deviation of the population. That's part of our formula there, in order to understand the standardized distribution of the sample means. Because we're now trying to estimate two parameters, we're introducing more variation to the standardized statistic, thus the distribution follows a little bit different of a shape. Now it still looks relatively normal, but if you look here, we're talking about this thing called degrees of freedom, but when we're dealing with means, there ends up being a little bit more in the tails. So that red line on here shows a little bit more space under the tails. So it is, if you have to use z, it's going to be okay, but it's not like a standard normal. It's going to look a little bit different than a standard normal distribution, which is why we're going to use this thing called a t-shape. or t-distribution. So not all mound shape or symmetric distributions are exactly normal. Excuse me. So we're going to get into a thing called a t-distribution. Now, what I'd like you to do, if you have your gold sheet, I have this here, you can pause this and try to include this at the top of the second page. This is some of the summaries of what we're going to be doing with confidence intervals for means. Okay? And I'll explain some of these in more detail in just a moment, especially that T star. But if you want to pause it here, you can write this down. Basically, this is going to be a one sample T interval for a mean. And we want to state the parameter. I have that at the bottom there. Mu equals the true mean of blank of blank. Conditions are going to be the same. We need a random sample from the population, normal distribution, and again, key points I'll have it's noted over on the far right. And if sampling without replacement, we need that 10% condition. Formula: x bar plus or minus t star times s, so that's that standard deviation, over square root of n. At the bottom there, that df stands for degrees of freedom. We're going to talk about that in a second. But that's something you'll have to state with the formula, what degrees of freedom we're using. Then we can find the interval, so I should probably add that here. This is interval. Not sure why that disappeared. And some key points. So one of them we want to make note of is this confirming the normality or approximately normal. If its population is normal, we're good. If the central limit theorem is good, or option number 3, and I want to make note, that's our last resort, is to kind of plot a rough sketch of it, and it's okay to proceed if there's no strong skew or any outliers from the sample data. We are using t-values, so there's a t-table on your formula sheet. That is, I believe, table B. So we've been working in table A, the t-table, this table B. And there's also this thing called inverse t on your calculator. We're going to talk about those as well. It's okay to use a z to find the sample size if needed, but we'll get to that at a later time. So it is close to normal. Now, finding t star. This is something that I want to talk about. You will be given a confidence interval, so just note that. Or confidence level, I should say. If we're trying to find a certain confidence level. So when we look at that and we look at our normal distribution, it's not so normal anymore. There's actually a little bit more space in those tails. But if we're doing a 95%, we're still looking for, this is 95%, we're still looking for what would be in the tails. In this case, this is each going to be 0.025 or 2.5%. Now if you find one of them, you can find the total out there. But that'll help you find that z or t value that makes the cutoff. So we're going to be looking at another thing you need to know is degrees of freedom. You'll see on your, whether you use the calculator or you use your table B, you need to know the degrees of freedom. And for one sample t intervals, it's always going to be, and you can state it like this, degrees of freedom is n minus 1. Whatever that n minus 1 is, that's what we're going to be doing. So find your sample size, subtract 1. So there's really two different ways to find this t value. Find this t star value. First way is use table B. Okay? So let's find the critical value. In this case, it'll be a t value, t star, for creating a confidence interval for a mean, making sure to state the degree of freedom you are using. So let's just say we have n equals 15, and we have the confidence level that's 98% confidence level. So I'm going to state right away, degrees of freedom is 14. Now I need to go to my table, and if I'm looking for 98%, this is kind of the visual of that table. You can see up at the top and at the bottom, there are the confidence levels. Okay? But it's actually not the, well, actually, sorry, the bottom has the confidence level, the top has the tail probability, but they match up. So if you look at, we just said the tail probability of 0.025, that should match up with 95%. And if you go down, that was the 95%. So you can use either way. You can look at either route. They kind of match up. So if I'm doing a 98% confidence level, I'm going to go to this one, which means the tail is going to be 0.01. So if I go up, that's the tail of 0.01. So depending on how you're looking. And then you know how to match it up with degrees of freedom. Okay, we said the degrees of freedom was 14. So if I go over here, play a little battleship, I get to a T star of 2.624. So I would say here, my degrees of freedom was 14. My T star equals 2.624. Done. Okay? Now, for the second example, technically my degrees of freedom will be 49. But if I go to my table, there is no degrees of freedom of 49. We never want to round up because it's not fully 50. So we would always round down. Okay? I'm going to make note of this. For degrees of freedom, never round up. And you always want to use, write the degrees of freedom that you used. So the closest one below it was 40. So I'm going to state not 49. I'm going to say the degrees of freedom was 40. So I go to my table and I do a degrees of freedom of 40, and it was a 95%. So I'm going to go to 40. So it's going to be closest down here. 95%, which would be 0.025 in your tail. That brings me to 2.021. So I would say, whoops, sorry. My degrees of freedom is 40. My T star is 2.021. Now, if you did this with a Z value and you found your Z star, it's going to be relatively close. What did we say? 1.96 is for 95%. So it's close. This just makes it a little bit more accurate for means. Okay? We got one more. Why don't you try this one on your own? N is 9. Confidence level is 90%. All right, degrees of freedom was 8. That gives us a T star of 1.86. So again, you must state the degrees of freedom when using the table so we know what you used and where it came from. Now there is another way to find that T value, and that would be using inverse T from your calculator. Okay, so why don't you go to your calculator and try to find inverse T right off the bat here. Now, it says use inverse T to find the appropriate critical value for creating a confidence interval for a mean. Make sure to state the degrees of freedom. Okay, so if I use this first one, I know my degrees of freedom are going to be 40, which would work on my table, but I'm going to use inverse T. In here, to find it, again, it's that idea that we're looking for, in this case, 97%, which means the tails would be 0.015, so it's 1.5% in each. That's what you need when you're using inverse T typically. So if you go to your calculator, pull it up here, and you go to second vars, so I'm going to go second vars, I can find inverse T as number 4. Now, it does not, I don't think it'll ever give you the middle like it does with like inverse norm. So you have to do your area, which would be to the left. So whatever the left, so I'm going to do 0.015. That would be the tail area. My degrees of freedom is 40, and then I can paste it in there. If yours doesn't have the option for the screen, you have to know that you have to put it in the 0.015, comma 40, enter. I got negative 2.25 essentially, which means the T star value would be 2.25. Negative or positive, it doesn't matter. You could have done tail to the right, but it would have been, this one doesn't work to the right. So the T star is 2.250 if you want to add that 0 there. Okay? That would be from inverse T, 0.015 and 40. Yeah. So tail, whoops, and degrees of freedom. So I should go ahead and try that with each of these two. Now the benefit of these is you don't have to, like, you can get the exact degrees of freedom. The table only has exact up to, so many digits, so you'd have to go to the lower one like we did with that last example. We went down to 40. You can do exactly 49 when you're using n equals 50 for this one, so you don't have to go down to 40. It's a little more precise when you have it on your calculator. But two different ways, you just have to do both. Or know how to do one of them, I should say. It's good to know both, but you got to be able to do at least one of them. So we're going to work on one confidence interval here. Confidence interval. And this is dealing with fast food French fries. All right, so we're going to work through the steps for this one. Scratch that. I'm going to jump straight to this one. It says a simple random sample of 20 male Great Danes in the American Kennel Club, AKC, was taken by a veterinarian. The weights are listed below. Find a 98% confidence interval for the true mean weight of AKC male Great Danes. Now, unfortunately, we don't know a lot of the information we need for this one. But we're going to go through the process here. Mu is going to be the true mean weight of the American Kennel Club male Great Danes. All right, got that much. We want to check the conditions. So in order to check conditions, well, let's do it. So first one, do we have a random sample? Of Great Danes. The American Kennel Club. Well, if you go back to the problem, it does say they have a simple random sample of 20 male Great Danes, so this is stated yes. Number two, we want shape. Now, unfortunately, it says nothing about the population shape. We only have 20, so it doesn't meet that condition. It's not greater than 30. So we have to go to condition or option number 3, where we actually have to draw it. So do we know if there's approximately normal distribution of the weights? So how do you draw it? Now, you have to use the data. I'm going to say make yourself a stem and leaf plot, a really rough sketch of one. These are all in the 140s to 170s, I think. So I'm going to do this. Oops, that's a 7. There's my stem. I don't even need to write the exact leaves. I just want to know, is it going to look? So instead of writing 140, putting 7 there, I just want to know how many are in the 140s. And I've got 1, 2, 3, 4. Again, the numbers don't really matter because we're looking for the shape. If I'm looking in the 150s, I see 6. So I'd have 1, 2, 3, 4, and then 2 more. 160s, there's 7, if I'm counting correct. And then 180s, or 70s, there's 3. So it's not perfectly normal. It's not a perfect T distribution, but it is enough of a normal curve that we can say we're going to move on and go along with this, because there's no, I'm going to say no strong skew clear outliers. That means it's okay to proceed. Now that was just one sample, but we don't know anything else about the population. So it's good enough to move on. And is 20 going to be less than 10% of all male Great Danes? I don't know if we know enough about it, but it seems like it's a... I mean, it says the American Kennel Club, so we're going to say that we assume yes. So if we take those conditions and we say they're all met, I'm going to make them all shrunk a little bit here. Then we're going to keep going. So there's our conditions. All right? Now, this is going to be a one sample T interval. We want to specifically say for means. And we're going to use the formula x bar plus or minus t star times the standard deviation over the square root of n. Now, here's the thing. We don't know x bar. We don't know the standard deviation. We don't even have a t value. We have n. We got to find the rest of them. So how do we find it? Take all this information, put it into one variable stats on your calculator. If you do one variable stats on your calculator, you can find the x bar was 159.15. The standard deviation, 9.405. And we have n already. We have to do that. T-value. Or T-star. From table B, I got, with a degrees of freedom of 19, I'm going to state that, I got 2.539. You can use it with inverse T as well. Now that I have all those things, I can plug in and do this. So I would be finding 159.15 plus or minus the T star, which was 2.539, times 9.405 over the square root of 20. There it is. Do a little simplifying. Calculators are helpful. I would get 159.15 plus or minus 5.34, which gives us an interval between of mu being between 153.81 and 164.49. There is my interval. Then I want to interpret. Okay. So, I can state at the, what did we say, 98% confidence level, or level of confidence, I believe the true mean weight of American Kennel Club male Great Danes is between 153.81 and 164.49 pounds. There's my conclusion. All right? That is a one sample T interval for means. Now, I do want to just really quickly go back to this example because all it asks is, are the conditions met for constructing a confidence interval? So it says a nutritionist randomly selected 8 fast food restaurants and found that the number of calories listed for small French fries are the conditions met. Now, again, our conditions for this are 1, random sample with context, Okay, this one is met. Of fast food fries at restaurants. Sorry, my context is weak. But yes, that one was met. This is the one I wanted to get to, the normal distribution. We don't know, like 8 is not greater than 30, or equal to 30. We don't know anything about the population distribution, so we have to draw it out again. And this is where you might benefit from making yourself a plot. Oops, sorry. We're looking for approximately normal. Again, need to plot. So if you're going to plot it and you have yourself like a little stem plot, we've got 200s, 300s, 400s. We don't even have 400s. We have 500s. So I'm going to make this, let's go by the hundreds. 2, 3, 4, 5. There's 3 in the 200s, 4 in the 300s, none in the 400s, and 1 in the 500s. And because this is a potential outlier, we're going to say this is not met. We don't know anything else, and this isn't even fully met, so we have a potential outlier. So we can't say that this condition is met, even with our third option of plotting it. So then, if you go into this, you could do your step 3. That one actually worked out. Is 8, less than 10% of all restaurants, or fast food restaurants. We'll assume yes. But that middle one was not met. We don't have an approximately normal distribution, so we can't use a Z or a T distribution. Okay, so that's what it looks like if it's not necessarily met in any way. That's another key part of what we're doing with confidence intervals, and that was section 10.1a. I apologize for the long video, but this is some new stuff in here. Our next 2 will be a little bit shorter. All right, we'll see you next time.